this is Patrick O'Shaughnessy, and I will be discussing statistical analysis techniques in this 5-part module associated with the InTERACCT series. This first part will focus on descriptive statistics. The learning objective of this part of the module is to allow you to be able to evaluate exposure assessment data using descriptive statistics. Therefore, this will be a primer on statistical methods, starting with the most obvious and basic level concepts. Listed here are some simple data characteristics that can be calculated for every set of observations. We are familiar with the average and a minimum and a maximum, and from that we can determine a range of all our data values. The concept of data variation is enumerated by calculating a standard deviation. And then there may be the type of distribution that the data values exist within. I'm going to give all examples utilizing Excel and its statistical capabilities. To take full advantage of those features in Excel, you need to activate the Data Analysis tool pack. It's not loaded automatically when you pull up Excel, and so you have to work through the options as shown to make it available every time you get back into Excel on that particular PC. On the top left corner of Excel, you will see File, then go down to Options near the bottom of the left column to choose from, and then click on the Go button associated with Manage. A window will pop up allowing you to click on the Analysis tool pack as shown here. It will then appear on the far right of the Data tab in the ribbon. The various capabilities to choose from within the Data Analysis tool pack are shown here. The window cannot be expanded, so 2 views are needed to show all the options. You'll see they are listed alphabetically from ANOVA analysis to correlations, covariance, descriptive statistics, histograms, moving averages, regression analysis, and t-tests of various types. So there are lots of extra capabilities within Excel via this tool pack. As an example, it's difficult to create a histogram which demonstrates the distribution of your data values because you have to first sort your data and then choose the number of your data values that are within preset ranges. But this is done automatically with this feature. Then, as shown, you can develop a bar chart of them. To start, you first have to establish the values that separate one bin from another in a column as shown, the bin range. For example, here bins between 1.2 and 1.45 by every 0.05 were created. Then the data values are entered in the histogram drop-down window, and then the output table will be produced, which will repeat the bin values again, as well as the counts within each one. Then, for example, a bar chart of number of worker within each bin grouping can be produced as a 2D column chart in Excel. However, using that chart type, Excel places the bin cutoff values below the bar rather than at each tick mark, as shown there. So it's a little confusing as to where one value starts in a bin and the ending value of the bin range. But note that by default, Excel places values in bins such that they represent numbers greater than the previous bin number and less than or equal to the bin number under each bar. Another nice feature available in the Data Analysis tool pack is this function called Descriptive Statistics. With this feature open, all data values are highlighted as the input range, and then the output range, a cell where you want them to go, is chosen. Finally, an option needs to be chosen which is typically summary statistics, as you see here checked off. The output for the data in column C is shown in column E. So very quickly, it gives you a variety of statistics: the mean, the standard error, median, mode, standard deviation, and sample variances. It also provides this concept of kurtosis and skewness, which gives an idea of how close the distribution is to the normal distribution, that's kurtosis, and how skewed the data is. In other words, not evenly dropping off on either side of the hump, as in a classic normal distribution. Finally, the range, minimum, and the maximum, the sum of them all and the count of them all is given. What it doesn't do is provide the functions used to compute each statistic, so you only get the constant numbers themselves in this table. But again, it's a great way to get a lot of statistics very quickly on your data. To get back to the concept of central tendency, this is the statistician's term for the best indication of the middle of the distribution. And here are three different ways of thinking about that middle value. One is the arithmetic mean, or average. As shown in the equation, the mean is the sum of all the values divided by their number. This calculation results in a value in the middle of the distribution of all values. And here, what I mean by middle, I'll show in the next slide. The median is truly the middle value after you sort them all low to high. For example, if you have 21 values, then the middle value will be the 11th one, so that there are 10 above it and 10 below it. If an even number of values, say 20, then the median is the average of the 10th and 11th values. The mode is the value that occurs with the greatest frequency, so it represents the peak of the distribution. To look at these indicators of central tendency graphically, a slightly skewed distribution is shown. Interestingly, the mean is ultimately what is referred to as the point of balance of the distribution. If you cut a piece of paper out having the shape of the distribution and then put a pencil underneath it to balance it, the pencil point will be placed on the mean value. So, for example, one problem with highly skewed data, say the prices of homes in a city, there will always be a few homes that are very highly priced relative to many others, more evenly priced homes. So the few homes that are high priced are far removed from all others, which pulls the average further to the right and is not necessarily then the best indicator of central tendency when there's skewness in the data. However, the median, as shown here, truly separates the area in half because the middle value is where 50% of the values are below and 50% are above it. So it necessarily has to separate the distribution evenly, 50-50% as shown here, and may be a better indicator of central tendency when the distribution is skewed. And then you see the mode is the value that occurs most frequently and is associated with the peak of the distribution. And as a side note, for a perfectly normal distribution with no skewness, the mean, median, and mode will all be the same number. To indicate data variation, the simplest way is to compute the range of all values. However, again, with skewed data, the maximum may be much higher than most of the other values. Therefore, the range will be very large relative to really the amount of variation that's in most of the data. Therefore, the more complicated way of looking at this is really a kind of average of the difference between the value and the mean of all the values. However, if all the differences are summed up of the mean from their values, that sum will be zero. All those differences of values below the mean will perfectly negate all the differences above the mean. So to get around that problem, they decided to square the differences, which makes them all positive terms, and their sum will be non-zero. So that's why you see in the equation here, y, the data value, minus y bar, the average, squared. But as shown in the equation also, they are divided by the sample size minus 1. It's a fairly long explanation as to why the sample size minus 1, but the easiest way to think about it is that the average shown here as a y with a bar over it, it's not the true mean. It's the average derived from our data. And our data is just one sample from an entire population. We never really know the population mean. So it has been discovered that these differences of the data values y from the sample average, y bar, those differences are smaller than if the true mean was used to compute the differences. So to compensate for potentially computing a variance lower than it should be, that sum is divided by a smaller number to boost up the sample variance to a value closer to the true variance. And that's by subtracting 1 from the sample size. Now, another problem with the variance is that it has squared units, of course. So, for example, if the y's represent airborne measurements in units of milligrams per cubic meter, then the variance is going to be in milligrams per meter cubed squared, which is not very convenient. To obtain a measure of the spread of the sample data in the same units as the mean, therefore, we can just take the square root of the variance to get back to the real units. So that's exactly what is shown here. The new value is known as the standard deviation. It's called the standard deviation because this equation has been adopted for use by just about everyone, and so is the standard way of determining variability about the mean of the sample. And in the next part of this module, we'll discuss the normal distribution, the distribution of the means of samples, and the concept of a confidence interval. Thank you.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.